Oh, thanks for the invitation. So my name is Hugh. I'm a PhD student at the Gatsby unit. And today, I'd like to present on some joint work that I did with my supervisor, Peter Orband, my collaborator, Pierre Glazer at Gatsby, and Ryan Adams at Princeton University. And basically what we're doing in this work is taking a look at how Markov chain Monte Carlo algorithms are implemented in modern hardware and software, and trying to find more efficient ways or eliminating waste when implemented on modern hardware like GPUs. And we'll see that the techniques we introduce here can lead to order of magnitude scale-ups in implementation. Okay, so just to set the scene, one way of starting off things is to look at this canonical issue of estimating expectations, which appears in numerous problems in machine learning. So for our purposes, we'll work on RD. And in a lot of situations, you don't actually know the distribution in advance that you want to, what you don't have is full knowledge of this distribution so that you can use direct numerical techniques to just sample from it easily using software. And so to get around this problem, a sort of tried and tested formula for well over 50 years is to try to construct some kind of Markov chain that converges to this distribution pi. And so in practice, what really happens is if you have this Markov chain that converges to this distribution, the idea is that this chain is something that you can indeed sample from tractably, even if you can't easily sample from pi. And so for our purposes, this Markov chain will be embodied by this function denoted sample here. So you can think of sample as an implementation in software that takes in a current sample of the Markov chain and spits out another one. And so in practice, what people do, am I too close? I'm hearing okay, yeah. So in practice, just think of the idea is you want to sample from this distribution. And so what people do if they have this Markov chain at their disposal is they just iteratively use this implementation sample, and this sample function has the property that it will converge to pi as we draw more samples. And so we typically draw n such samples and estimate the expectation empirically. Okay, so that's one way of doing it. What we're going to look at is how to actually assess, how can we actually improve the performance of MCMC. So there are different ways of looking at MCMC performance. Obviously, there are many different Markov chains that you can construct that converge to a particular distribution. Those different Markov chains are different MCMC algorithms. Those in practice will have different properties. They might converge to the distribution at a different rate, and they might produce samples that are also correlated to a different degree. We're going to focus on the implementation side and ask, for a given MCMC algorithm, how can we speed up this algorithm in a way that produces, that increases the number of samples per second that we can draw? And so something that's well known is that MCMC, this task of drawing from MCMC algorithms is embarrassingly parallel. If you have M machines, you can just run M chains in parallel. And so if you're able to draw n samples per second, then now you can draw m times n samples per second instead. All right. And so the benefit of doing this is that if you want to now estimate this expectation, we can now pool all those samples together. And if you've run your chains for long enough so that the samples are roughly distributed according to this distribution pi of interest, then the variance of this estimator should hopefully decrease roughly linearly in the number of machines. So this is one way of achieving speedups with MCMC. So vectorization is a similar thing, but it's the act of trying to get the most bang for your buck on any given machine that you run the code on, that you run the program on. So before you have M machines, you're running one Markov chain on each machine. Vectorization is the idea that we might be able to use hardware like GPUs more efficiently. These GPUs can typically run, they're very good at executing the same instruction on multiple data instances at the same time. And so because of that, there are machine learning frameworks such as JAX and indeed PyTorch and TensorFlow as well that implement these functions. So here I'm using the semantics of JAX, which is very popular in MCMC. And this function vmap basically just takes your code that you've written to draw, or rather to update a single sample, and returns another function that can now act on batches of inputs at the same time. And those batches of inputs, the number in the batch doesn't have to be defined. What's really happening is if your input is a vector, It now just has transformed your program to operate on a higher order tensor under the hood. And so that's, as I mentioned, this is very efficient because modern GPUs are very good at executing the same instructions for multiple instances in lockstep. And so here I'm showing an example where even just on one GPU, if we increase the number of the chains that we run using this vmap approach, we can broadly achieve linear speedups by increasing the number of chains. And this is up to GPU capacity. There are complicated reasons why at 64 chains we start to see a greater increase in variance, which we won't have time to go into. But broadly speaking, the idea you should have is that for simple programs like this simple MCMC algorithm that I've run, we can achieve massive speedups in samples per second by using these types of tools. But the problem is these tools are really a bit limited in how they actually handle control flow. So the algorithm I implemented here was a very simple straight line program that just involved matrix vector calculus. A lot of MCMC algorithms, and indeed other types of machine learning algorithms, involve if then else's, while loops, other sorts of conditional logic. And so the question is, well, if you want to send an instruction off to a GPU, if those instructions now differ for each batch member, how do we actually handle this? And there is this general paradigm that's emerged for various reasons. And that is this sort of run and mask paradigm of if I see an if then else, different batch members may end up on different branches. What we're going to do is just run all the branches for everyone. And then we'll just mask out the results. We'll store a mask, and then we'll just keep running. So we'll run all those branches, mask out things, and then we can continue to the next instruction in the program. So basically, the cost we incur is if there are two branches, we just have to run both branches all the time for all batch members. But this way, we can tap into the power of GPUs. All right, so that's how you handle an if statement. This same principle, though, has a big problem when it comes to input-dependent iterative control flow, like while loops. And that is that under the hood, you can think of a while loop as being transformed by these automatic tools into a single operation that has one termination condition. So before, you might have looked at a batch member and it says it runs its while loop under the hood to draw a sample for a certain number of iterations. If that number of iterations depends on the current place it is in the distribution space, then now this single loop that's created by these vectorization tools will essentially force all of the batch members to iterate until the slowest batch member is actually done. And so now at every step of the sampling procedure, all the batch members are waiting for the slowest. And so just to show you how damaging this can be, so let's actually look at a real MCMC algorithm that's quite popular. Hamiltonian Monte Carlo algorithms have been pretty much at the forefront of a lot of gradient-based Markov chain Monte Carlo for a long time. One variant of HMC, it tries to do a lot of the hyperparameter tuning under the hood, and that is the no U-turn sampler. The visual representation you should think of with the no U-turn sampler is that it augments your distribution with another auxiliary variable and tries to build a trajectory, called the Hamiltonian trajectory, through that space. And it does this using an iterative doubling procedure, so you can kind of see this procedure here. And what happens is at each step, it sort of doubles this trajectory, starts to integrate along the trajectory. And then at each step, it's checking for certain termination criteria. In particular, it's checking whether this energy that, we can't go into it now given the time, but the energy needs to be conserved in this distribution. So it's checking, because we use a numerical integrator, whether that energy is diverged. If so, we stop. It's also doing something called a U-turn check, which makes sure that as we're integrating along this thing, we don't end up turning back on ourselves. And the aim of doing this is to try to make sure that the next sample we propose from the Markov chain, whilst being valid, is a sample that is as far away as possible from the current sample. And that helps to reduce the autocorrelation in the samples and give more efficiency. So the point is, there's all these checks and balances going on under the hood, and these are implemented with while loops. And so now I'm just showing an example where we actually implement this algorithm, this well-known algorithm, on a simple problem of a high-dimensional correlated Gaussian. And what I'm showing on the bottom left is the distribution of the number of integration steps we needed before the algorithm terminated its criteria inside of this. So this is all to achieve the next sample of the Markov chain. And so on the left, what you can see is that basically with high probability, we take a very small number of steps. In fact, it's around 20 on average. But the probability that at least one chain needs to run for 1,000+ steps is almost 1. when we use 500 chain. And so basically, if you're using those current automatic vectorization tools, you're going to have to wait for the full 1,000 steps every time you draw a new sample. When in practice, the average number of steps, if these chains will run independently, would be far fewer. And the other aspect here is that it's not just the case that one of the chains is always slowest. If there was always one chain that was the slowest because of its random seed, and it was something deterministic, there wouldn't really be any speedups on the table. You'd always have to wait for the slowest chain to finish its samples. But what we've shown and proven under certain conditions is that actually, for a large number of algorithms, this distribution of the number of iterations is an IID random variable. So it is the case that if you just were to run these chains for long enough, the computational resources they actually use would balance out. And so I'm just visually showing that here for this algorithm. If we check the distribution of the number of steps per chain taken, it's concentrating more and more tightly around its mean. So it implies a central limit theorem here. Okay, so that's an example. The basic idea of what we do in this work is to try to relook at the structure of the algorithms. And in particular, what we want, so the goal is we don't want vectorization to be hard. We want to be able to use those modern tools, but we want to be able to use them in a way that doesn't incur all of these synchronization barriers. And so the sort of mental map of what we do is basically this function sample that is drawing the next sample of our Markov chain. What we want to do is break it down into a set of algorithm states. And hopefully those algorithm states have lower variance in execution time than the while loop, which is going to be the bulk of the variance that we saw. And what we want to do is, instead of trying to structure the synchronization that we do when we send instructions off to the GPU around the iteration number or the sample that we're on, what we want to do is structure the synchronization around the actual internal state of the algorithm instead. So here you can see, this is sort of the idea of what's going on. At each step, there's a sequence of instructions that we're sending off encoding the sample. And the fact that there are 3 sample boxes just reflects the fact that we may be drawing 3 samples from this Markov chain. And there are multiple chains. And so at a high level, what we end up basically doing is trying to break this algorithm down in a way that avoids using any iterative control flow. So here I've shown a simple example where maybe the algorithm, the sample function involves one while loop with some termination checks. And so the solution here is very simple. Just define code blocks above, during, and below the while loop. So we essentially use the termination criteria, but the while loop boundaries delineate these contiguous code blocks. And once you have these code blocks, we then have to just keep track of all the information those code blocks need. The whole sample function will have certain inputs, like so I showed you that it had the current sample. Each of these code blocks will have a larger set of inputs. Maybe code block number 2 needs the current log density at this point, or it needs to keep track of the current integration step. So we define these blocks, we take in these larger augmented set of inputs, and then we just need to make sure that we remember the logic of the while loops, which is encoded through this function delta. And altogether, this defines something called a finite state machine, which appear in automated theory. So this is just one example. In practice, there are more complicated programs. We do have an automatic procedure that kind of takes in a program like this and then can transform it into this supposed finite state machine formulation. Okay, so it's not clear. This is breaking the program down. It's not clear how this actually solves anything. The idea is now that we can define a new notion of what a step is under the hood. Before, a step is something that depended on the instruction. So it could be multiply 2 matrices together and then run this while loop until they're all done. Now, a step is defined at a more granular level, where each of these blocks is now a step. So for instance, if we have a program with 5 steps, we can now define an aggregate function that says, run me wherever the algorithm is for each batch member, just run that state. And then using the internal logic of the while loop, which is encoded through another function, delta, tell me where to go next. And that's shown in this very simple algorithm on the right-hand side. In practice, we're using a switch, which is essentially a type of if-then-else under the hood that just says, given each batch member, run the appropriate block that it's on, and then tell me where to go next based on whether the while loop is terminated or not. And so this seems a bit like we've just changed things around. But the crucial point is that now we don't involve any iterative control flow. And we can just run this algorithm repeatedly for every chain we want until we've recovered the number of samples we need per each chain. So that, somewhat ironically, uses a while loop. But the important point is that it doesn't enforce any synchronization until we've actually finished terminating after 1,000 samples. And most importantly, we can vmap this thing. So once you have this step function, you can just vmap it as normal. And now you can run and no synchronization barriers hold. Okay, and just, yeah, slightly misleading illustration. So, here's this idea that, so we start off, if we were to start off some chains, if we sort of visualize what's happening, this structure of these states, they exist no matter whether you've used our finite state machine approach or not. They still are a sequence of instructions under the hood. When you run our algorithm, let's say that batch member number 2 is going to take a long time to compute its loop iteration. So if they're stuck together, as in the FSM case, they're going to have to sit there together. But in our case, each step is just one call of these states. So we run this once, the first batch member can progress on to S3, and so on and so on. Then maybe the first batch member now gets stuck at S2. Now this one is done, so they progress forward. But now, because of the random seed, this one for the non-FSM has to wait, but our one is actually finished earlier, and so on and so on. And so the idea is basically that by avoiding waiting for everyone at every step, we can achieve quite large speedups. Okay. Yeah, okay. Well, then I'll just finish by saying that we do some theoretical analysis here. Essentially, what we show is that there is a theoretical upper bound on the speedup. The basic algorithm I've shown you doesn't obtain that unless in special cases, but we do show how to actually refine the implementation of this design so that we can actually attain this theoretical bound in speedups. And then when it comes to the problem that I showed you before, as an example, we can actually achieve an almost 10-fold speedup implementing HMC-NUTS on this problem. What's important to note as a finishing statement is that the solution we propose here doesn't actually change the fundamental maths or statistics of the sampler. It's just about being able to get a much larger effective number of samples per second out for the same algorithm with the same performance. So I'll just conclude by saying thank you to my collaborators. If you're interested in this kind of software or think it could be useful to your research or tangential problems in machine learning, we do have a GitHub repository, and we're going to hopefully work with some of the people at JAX and Blackjacks to build this into MCMC libraries. Okay, thanks.
Thank you.